Thank you very much. Thanks to everybody here in the room and online for joining us today. I'm Zach, and I'm going to talk to you about some work we did on the RISE 2 survey node during the last field deployment this past spring with the Artemis 3 baseline handheld camera. When we talk about that, we're referring to this, which is a Nikon Z9. It's a mirrorless digital camera, 48 megapixels, essentially a high-end, off-the-shelf camera that has been selected to be included on the Artemis missions. With a bit of adjustments to its software, it's essentially a consumer-grade camera. You can see it here in a recent analog test. This is the Jet 5, excuse me, analog test in the hands of the astronauts out in the field. And you can see it here with us in RISE 2 in the hands of a couple hopeful future astronauts doing some field work. Kilburn Hole was the field site. It's a big Mar volcano. It's some magma rose to the surface, interact with the groundwater. You get a big steam explosion, and it excavated a large crater, which is now geologically and morphologically analogous to the lunar surface. So we use this for some testing of just so we could get to understand how the camera worked, to understand how it would work on future EVAs, and also to do some tests with photogrammetry. For those of you who don't know, photogrammetry is sort of the science of how you can take measurements using photographs. When you take a photograph of a target, say a big conglomerate rock, you're collecting a field of view of light that enters the camera lens. And if you shift the position of the camera a little bit to a different angle, you can collect a second field of view and then do a bunch of math to work out the positions of where those cameras were in space, and then how large and what distance away objects were within those field of views. So what this looks like in practice, if you look at that same rock and you take a bunch of photos, we'll start with a simple case of just two photos, a stereo pair. And apologies, this next slide jumps around a little bit to show those two photos. So if you're photosensitive at all, just avert your eyes for a second. But if we take a couple different photos of this rock, you can see a few different, two different perspectives, and the background changes a bit as well. When we plug that into some software, we use a program called Agisoft Metashape Pro, you can get this. The two blue boxes in the sky there represent the location of two photographs, and then the 3D model you're seeing is a combination of those two fields of view. You can see the rock in the foreground, a lot of terrain detail in the background, and then also a lot of shadow where those two images did not collect information about the rock. Obviously, you couldn't see the whole rock with just two photos. But if you increase the number of photos you collect, say to several of them, hopefully the animation plays, there you go. You can see multiple perspectives of that rock, and you can build a sequence of photos that looks something like this. This is 96 different photos. This is sort of your classic, if you're taking a class on how to do photogrammetry, they tell you take as many photos as you can from as many angles as you can, put them together, and you get a very dense model. This is a point cloud that has almost 100 million points. You can see all the individual rocks in the big conglomerate there, and a lot of the terrain surrounding it. So with this detailed photographic analysis, you can do things like grain size analysis, you can measure the distance between features in the scene, you can even see some footprints in the foreground, so you could do some compaction analysis of regolith, that sort of thing. And this is just a point cloud. All the lighting is baked in from those two photos, or from the series of photos that were collected. However, taking 96 photos is a big task, and it's not something you would want astronauts on the moon surface to be spending their time doing. So the question we were asking during this test is how few photos could you get away with, or more precisely, how much time would you want to dedicate to this type of activity during a lunar EVA? And so here you see two examples using the same rock. The one on the left has 16 photos as opposed to 96. The one on the right has 8 photos. And then these two animations will sync up in a second. You can create fairly comparable models using that number of photos. The big asterisk here is it's not the number of photos we're concerned about, it's the amount of field time dedicated. So with 16 photos, you're looking at about 1 to 2 minutes of walking around, taking those photos. 8, less than a minute. We weren't wearing suits or anything, so there's the caveat that actual astronauts might take a little bit more time to get in position. But with a small amount of field time, analogous to time dedicated to other sampling techniques, you can get fairly robust models of interesting targets on an EVA. You might think that this is a pretty diverse target. It's got all those little clasts in there. Would it work with something else that's a bit more monochromatic? And in short, with example 2, this basalt boulder, the answer is yes. We were able to create a pretty good model. This one took a little bit longer because there was a bush in the way. You have to kind of walk around obstacles. And so with 96 photos, you can create a really, really good model of a boulder. Or you could, but I've been a bit tricky here, and this is actually a model that you're seeing that was made with just 18 photos that took between 1 and 5 minutes to collect. So again, same timeline of taking a panoramic sequence that is already worked into EVA for Artemis, or collecting a geologic sample. Photos of individual targets are not the only thing you can do with this technique. Kilburn also features surge beds, these ash deposits that were in place when the volcano erupted. And so Marie, my co-author, went along and took a sequence of photos along the outcrop, facing the outcrop, and was able to create a pretty robust model of the entire stretch of surge bed. We'll kind of orbit around here. You can see, again, the lighting is baked in, but you can get really detailed representations of the thickness of these beds, the way they sort of dip and weave, and even start to do some measurements in there. We actually call this, jokingly, the most observed outcrop in the solar system. We've hit this with a bunch of different LiDAR techniques and a few different photogrammetry techniques over the years with RISE 2. So if you really want to know an outcrop very well, this is the one to study. And you might be a bit ahead of me here, but if you're thinking, if you're walking along an outcrop taking individual photos, you might be able to streamline that by just taking a video and then looking at individual frames as you're traversing. Fortunately, the Artemis astronauts and our analog astronauts in the field have suit-mounted cameras. You can see the small blue box mounted to Jose Hurtado's chest there as a GoPro camera. And so we did a few tests this last time in the field where we had some structured traverse paths, and we selected individual frames from video to, again, put together structure from motion models. So we did a few different tests, one where Jose just did a straight traverse from A to B across the field of boulders, one where Jose walked out and back, so you would get both sides of any rock that you see in the field, and then a series of tests where Jose did a bit more of a natural geologic investigation of a field site, walking around rocks, sort of not thinking about the camera itself, but how you might move if you were looking at potential targets. And again, this next, we got some audio too. A bit busy here, a bit jumpy around, so apologies for the video quality, but a bunch of good frames. Again, this is high definition, I think 4K video footage. What we get back from the astronauts at first won't be this high resolution, so that's a big asterisk on this test. But from this data, you can pull out individual frames. And what that looks like is this. Each blue box represents a frame about half a second apart from that video stream. And again, there's no GPS data here. This is just relative position of the camera. So you can not only tease out the shapes of the rocks on the ground, but the path the astronaut took based on the video footage. And what this looks like with just the straight out and back from A to B is you get a model of that traverse path with all of the larger rocks showing their texture and things in the direction that was shown towards the camera. Everything away from the camera was in shadow, not collected, and represented by a blank space in this map here. In the more sort of advanced or natural exploration of this same field area, you can see Jose walked around, did an orbit of some rocks, and then kept going. Which is interesting enough that on the moon you won't have GPS. So if you are using just that video feed and some careful analysis, you can figure out the exact path they took. But you'll also get these beautiful models, especially in the center where you had all of those overlapping frames. You now have very detailed representations of those boulders. You can see we put down a scale bar and a photo color chart as well, just for some other tests. So you can work out the exact size and distance of each of these rocks. Which, if you're looking at a few different things to sample, and you might actually collect a sample here, this helps put that sample in context, and it also puts in context the other rocks that you might not have chosen to sample. So where do we go from here? We actually, if you've been to Survey before, we've had several years of RISE 2 field operations, including in 2023, when we had a set of 4 pairs of analog astronauts do a bunch of field work out of Kilburn Hole. And so what you're seeing here on the left is Marie and Matt Svensson. They were one of our astronaut pairs. And on the right are 2 of our adjacent EVA stations. And these very colorful lines represent the traverse paths that they took. We were able to get these because those GoPros did have GPS signal in there. So these are sort of the GPS tracks. But they also represent recorded video tracks.
1 minute.
1 minute, perfect. Of where the astronauts walked. So we haven't analyzed these yet, but we have a ton of video footage, and we're hopeful that within the next year we might be able to put together a very dense DEM of our EVA stations, just based on passive video footage. And so we'll wrap up with the conclusions here. To make it succinct, the 4 conclusions are to make sure you train, plan, execute, and support. Train the astronauts to know when a good situation to take these sort of multi-view stereo photos is, and even team members so they know what they might be receiving on the ground. Plan traverses that can show you potentially future stations or do a good job of walking along a current station so you can just get that passive video footage and passive DEM models. support, make sure you have a bunch of team members on the ground and enough computing power to process these so that during an EVA you might be able to turn these models around. And when you're executing, you can get pretty good models in the same amount of time as is dedicated to other EVA activities. With that, I'll leave it there. I'll just say thank you. And those are our emails. We're happy to collaborate in future projects. So thank you.
All right, thank you. Our next speaker is Mark Schellhammer, and the title of the talk is The Synergistic Role of Humans and Machines in Autonomy and Mission Resilience.